Good afternoon. My name is Clayton Cushing, and today we'll be talking about how quantum computing will change the world as we know it today. Computer processors have found their way into nearly every facet of our lives today. Take a second to think about it. Everything from our phones, our cars, our TVs, watches, glasses, and scientists are even talking about integrating computer chips into contact lenses. In today's society, the computer is everywhere. The computer hardware industry is one of the quickest growing markets on Earth. At its core, innovation in this industry is driven by the constant improvements in the field of microchip technology. Now, a microchip is a small circuit board in a computer that's responsible for performing the logical processes of a computer. Over the past several decades, the size and speed of microchips available has been drastically improved. And these improvements are what's responsible for a myriad of different technologies that we use every day. Modern computers work by translating data into what's known as binary code, which is a code of ones and zeros to represent numbers and characters. On the computer, a 1 is represented by adding a charge to a device known as a transistor on the microchip. A transistor without charge represents a 0 in binary code. With data in this format, the computer can then perform logical operations. Now, in order to create better and faster microchips, it's necessary for scientists to create smaller transistors. The smaller a transistor is, the more that can be fit on a chip, and the closer together the transistors can be positioned. This both increases the computational capacity per size of the computer chip, but it also decreases the time it takes for the transistors to communicate with one another. Luckily, the trend of decreasing transistor size has been pretty consistent throughout the history of computer hardware. In fact, about every 2 years, the number of transistors per square inch that can be fit on a microchip has doubled. As you can see here, early transistors started out nearly 4 centimeters in length, whereas modern microchips, such as this one being held by an ant in this picture, contain up to 30 million transistors. Now, the phenomenon of decreasing transistor size is known as Moore's Law, and it's held true for essentially the entire history of computer hardware. But unfortunately, Moore's Law, which has been driving computer innovation for years, simply can't be true forever. Simply put, once we get to the point where transistors are the smallest they possibly be, then we can no longer keep increasing the number of transistors on a chip. Now, theoretically, the smallest a transistor could ever be would be a transistor made from a single atom. And it certainly seems far-fetched and futuristic to be building computer hardware components using only a single atom, but the reality of it is that it's much closer than you may believe. In fact, researchers at the University of New South Wales have already created transistors using single large phosphorus atoms. Now, these single atom transistors are still a ways off in terms of commercial implementation. But one thing is very clear. We are quickly reaching the boundaries of what can be done with current microchip technology. And if we want to increase innovation in this field, we must find a whole new method of computation. The emerging field of quantum computers seeks to fill this very role. Quantum computers are beneficial in the way that they perform computations. Now, a standard computer today, as I mentioned earlier, denotes binary code with ones and zeros on a transistor. A quantum transistor, however, can represent both a 1 and a 0 at the same time. Now, this concept is difficult to wrap your head around. You may have heard of the analogy called Schrodinger's cat. Schrodinger's cat is a classic thought experiment that seeks to explain quantum concepts by relating them to the real world. Now, suppose you have a cat, a sealed box. You can't see in the box, and you can't hear the cat in the box. Now, inside that box, there's a canister of poison gas, which over an interval of time has a 50% chance of releasing and killing the cat. Now, while the cat's in the box, you don't know if it's alive or dead until you open the box and check. At this point in time, when you don't know if the cat's alive or dead, from your perspective, that cat is in a position of superposition. It's in both states at once from your perspective. When you open the box, you observe the cat is either alive or dead, and it takes on a definite state upon observation. Now, of course, for the macroscopic world we live in, Schrodinger's cat is a metaphor. A real cat is either alive or dead at any given time. However, in the quantum microscopic world, Schrodinger's cat in superposition is a very real phenomenon. And any given quantum particle can be in as many as 7 different states at the same time. Furthermore, the state a particle is in is relative to the position of the observer. So while the particle could be in one state relative to a certain observer, it could in fact at the same time be in a different state relative to a different observer. The concept of superposition is incredibly important with regards to quantum computing. Modern computers think linearly, which means they perform calculations one step at a time and one after the other. A quantum computer, however, can perform multiple calculations at the same time. This is because the particles can be in a superposition and be in multiple states at the same time, which means they can be utilized in multiple computational processes simultaneously. Because of this, quantum computers can run at speeds exponentially faster than modern transistor-based computers can. Say you wanted to travel from New York to LA, and you're going to use a computer to calculate the shortest possible route. If you used a standard computer, the computer would map out each of the routes from New York to Los Angeles, it would put each of these routes in a list, then it would compare the size of each route in the list and return to you the shortest possible distance between New York and LA. A quantum computer, however, could simultaneously evaluate all of the different routes and then give back the shortest distance, all in one computational process, with the particles acting in multiple states at the same time. A modern computer, on the other hand, would have to do a separate computational process to map each route, and then a further computational process to compare their distances. It just doesn't compare in the speed at which the algorithms can run. Now, the speed increases that we see with quantum computing could have massive implications in many fields in science. Because quantum computers can perform at an exponentially faster rate than normal computers, simulations that would have previously taken days, even on supercomputers, can be done in a matter of minutes or even seconds on a capable quantum computer. An example of an application is protein mapping in the medical field. Currently, protein mapping is a very difficult and computationally intense process that takes a long time. However, with a quantum computer, an individual would be able to map out somebody's specific proteins and create medicines customized to that specific individual. This is something that's not currently possible due to the limitations in computation that it takes in order to map out proteins. Furthermore, quantum computing could have massive implications in the field of code breaking in the military. Currently, code breaking is done using a technique known as brute force attacks. Essentially, the military will take a supercomputer and repetitively guess answers to a code over and over, millions of them per second, until finally it reaches one that is correct. As I mentioned earlier, modern computers think linearly, so the computer has to guess and check each of these possibilities one after another, one at a time. A quantum computer, on the other hand, could simultaneously evaluate multiple different scenarios using the same subset of particles, allowing the computer to break codes at an exponentially faster rate than even the strongest supercomputers today could have. Ultimately, we are running out of room in the field of computer hardware to innovate the computers that we have today. However, with quantum computing, we'll be able to revolutionize the entire field and break down the barriers of what can and can't be computed. Much like the silicon computers that came before them, quantum computers have the ability to change the very world as we know it today.